Hey folks, in this video we're going to be talking about a circuit property called inductance and a circuit element called inductors. So we're thinking about Faraday's law for electromagnetic induction and what it means for the behavior of circuits and in general, and also how can we use this behavior, how we use this in a useful way with circuits. So let's start with thinking about circuits and inductance. I have a very simple circuit drawn here. On the left is a time before t equals 0. We have an open switch, battery, light bulb. Then we'll close the switch, and we're going to think about what happens immediately after the switch is closed. There's a transient phase that happens, right? We get current in the end. We start with 0 current. The current must build up from 0 to that value, whatever it's going to be in the end. Let's think about that transition together. Using what we know now about magnetic fields. So to start, current's going to start flowing clockwise around this circuit, and the current's going to get stronger. It's going to build, it's going to increase. But we now know that moving charge is what creates magnetic fields. And so this current is going to create a magnetic field. The magnetic field, let's look at this section of wire right here. To the left of the wire is going to be coming out of the screen according to our right-hand rule. And on this side of the wire, it's going to be pointing into the screen. And in fact, if we follow that same logic all the way around our loop, inside of the circuit, the current is going to create a magnetic field that points into the screen. There'll also be a magnetic field outside of the loop that points out of the screen, but we're only going to care about what's inside of the loop because that's what affects Faraday's law. So we have this magnetic field pointing into the screen, and because the current's getting stronger, the magnetic field strength is also getting stronger. We learned that if you have a magnetic field that is changing over time, then it's going to create an electric field. And if you use the curl rule with your right hand, where your thumb points in the direction of the magnetic field into the screen, your right hand curls opposite the direction of the electric field that's generated because of the negative sign in Lenz's law. And so the electric field that gets created, if you follow that rule, the electric field around the circuit points counterclockwise. The magnetic field that the circuit created is also creating an electric field that pushes back against the current that's trying to flow. So we have this induced electric field due to the changing magnetic field, and it's pushing back against the current from the battery, IBAT. And this slows the rate at which the current grows compared to if there were no magnetic field. Of course, there always has to be a magnetic field, but if that weren't the case, we wouldn't get this pushback. And this pushback is called a back EMF. And the strength of that back EMF is equal in magnitude to the rate of change of magnetic flux, right? That's Faraday's law. So we get this pushback. And it's not going to prevent current from flowing around this loop, but it will slow down how long the transient phase is. The transient phase without it would be nearly immediate, and with it, it's going to take a little bit longer. But eventually, things will reach a steady state. Let's look at that steady state together next. In the steady state, the current from the battery is constant. The magnetic field that current creates is also constant. And because the magnetic field is no longer changing, Faraday's law tells us that it will not generate an electric field. A magnetic field is present, sure, but you need a changing magnetic field to generate an electric field in a loop of fixed area. And so the charge flow is no longer induced by the field. It is still by the battery, but there's no charge flow induced by the field, no more back EMF, no electric field to worry about anymore. So steady state's as if there is no back EMF, there is no inductance by the circuit on itself. In the steady state, that's only a transient state phenomenon. So here's the summary. During transient states, but only during transient states, you get these time-varying currents. These time-varying currents create time-varying magnetic fields. And we know that time-varying magnetic fields create electric fields that oppose the change. These opposing fields create a back EMF, It introduces what I like to think of as like lag and reaching. That's when they're reading. This should say reaching. There we go. Create some lag in reaching the final steady state. And we call this lag the circuit's inductance. All circuits have inductance. It's a property of circuits. You cannot avoid it. So sometimes it's a bad thing. Sometimes it gets in the way. Other times you want to delay the steady state, in which case you're going to put in a device called an inductor, which takes advantage of this property. So a device which purposefully introduces this lag is called an inductor. And it's represented by a coil in a circuit diagram. So you have inductance, the property, inductor, the physical object. The amount of inductance, the amount of lag you're going to feel to reach steady state is abbreviated capital L. L for lens, the same scientist as Lenz's law. The L depends only on the geometric properties of the inductor, much like capacitance depends only on the geometric properties of the capacitor, and resistance depends only on the geometric properties of the resistor. We've got capacitance in farads, we've got resistance in ohms, and we have inductance in Henry, capital H for the SI unit there. So we have a circuit diagram shown here. Right there is a 50 millihenry inductor. Why do we use a coil to draw inductors in a circuit diagrams? Well, this next slide has pictures of inductors. Here's what they actually look like. And as you can see, they're coils of wire. Why are they coils of wire? We want a lot of loops. Adding more loops creates more area for magnetic field to flow through and then to change through. And if you have more area through which that magnetic field is changing, you get more charges affected by those electric fields pushing back. On the left, we have several different varieties. We have a cylindrical inductor, we have a toroidal inductor, and others here that you might see in a circuit, which has stuff like these two hidden inside of boxes or other wrappings. Inductors are solenoids. It's just taken down to a tinier scale for your circuit. The picture on the right has a circuit diagram or a circuit board, with two inductors in it, and behind it you can also see two capacitors there. So let's talk about them. The back EMF, that voltage pushing back due to these electric fields from time-varying magnetic fields, the back EMF in an inductor is often directly proportional to the time rate of change of the current during that transient period. So that equation shows the voltage, the EMF pushing back because of the inductor is proportional to the rate of change of current. And the inductance is the constant of proportionality between those two. Negative sign because it's pushing against the change in current. Let's look at a concrete example. Here's our example. We're going to derive an expression for the inductance of an ideal solenoid. We start here. We have the magnetic field for an ideal solenoid. We derived this from Ampere's law. Mu is the permeability for magnetic fields of whatever material is in the core of your solenoid. If it's a vacuum or air, we're going to use mu naught, but if it's iron, we'll use whatever the magnetic permeability of iron is. So I dropped the subscript 0 there to indicate that it could really be any core material. N is the coil density, which I've expanded out below as big N, total number of coils, divided by L, the length of the solenoid. I'm using lowercase cursive l for that length because big L is now inductance. And then capital I is the current going through your solenoid. So we derived that earlier. Next, I want to look at what Faraday's law looks like in the case of constant area, because we're not making the cross-sectional area of our solenoid any bigger or smaller. So it looks something like this. The induced EMF is the negative of how many coils you have, big N, and then the rate of change of flux. Flux with a constant area is just field strength times area. Factoring that constant area out of our derivative, our EMF is opposing changes, total number of coils, area of the loops, the cross-sectional area, and then the rate of change of the magnetic field. And our definition of inductance looks like this. We have the back EMF is the negative of the inductance, and then the rate of change of current. It's opposing, negative, the change in current. So what does this derivation look like? Well, here is epsilon, here is epsilon, put them together. We have the negative of the inductance times the rate of change of current is equal to the negative of, from Faraday's law, number of coils, area, and the rate of change of the magnetic field. If we then substitute in the expression for the magnetic field of an ideal solenoid, factor out the constants, and we recognize that we have the rate of change of current di dt on both sides of the equation in purple here. So everything else L, this must be L. We have the permeability of our solenoid, the number of windings around the core squared, the cross-sectional area of our solenoid, and divided by the length of the solenoid. So there we have it. This is the inductance of a solenoid. So a few things I want to point out is first, these are only geometric properties or material properties of our solenoid. It's what we can do in the factory to build it, right? We can put a certain core material in there. We can wind it up a certain amount. We can make the area bigger or smaller. We can make it longer or shorter. But that's all we can do. And so these shows that inductance depends only on geometric properties. Let's think about why. How do we introduce more back EMF, more pushing back electric fields? If we make those loops bigger, that's going to be more flux through the loops. If we have more loops, that's more flux through the loops. And if we make the solenoid longer, we're going to have less of an effect, right? So we're not going to be able to push as much. All right, let's keep going. I want to think about what this looks like in a circuit. Based on the idea of this lag, that these inductors introduce lag, I want us to sketch current time curves through the resistor shown in the circuit below for inductors with first 0 inductance, then 15 millihenry, and then 30 millihenry. We'll say t equals 0 is when the switch is closed, and we'll annotate local max, min, and asymptotes. So we've got, what do we have? A battery, we have a switch, we have a resistor, we have an inductor. That's it. First, I close the switch, and there's no inductor here. What's going to happen? We know that almost instantly, the current's going to reach steady state. So no inductance, flat line, current as a function of time does not change. If, however, we introduce a 15 millihenry inductor into the same circuit, we're still going to reach the final steady state, but it's not going to be instantaneous any longer. The graph might look something like that builds over time. Double the inductance, 30 millihenry, it's going to approach the same value but take longer. All of these are approaching the same asymptote. That asymptote is just, the current is the voltage divided by the resistance of the resistor, like we saw very early on this year. So all approaching that value. Without an inductor, happens instantaneously. With an inductor, takes some time to stop. So that's what these graphs look like, what we call an LR circuit. I next want to look at a circuit that has an inductor, a capacitor, and that's it. There's no battery, there's no switch. All we've done to equal 0 is we've connected this circuit with a fully charged capacitor. So again, based on the idea of lag, we're going to sketch current time curve for this circuit, but we're also going to sketch a graph of charge time for the capacitor. And I actually really want you to take a moment now to pause this video, talk over with a friend what you think this will look like, and maybe sketch some initial ideas. So go ahead and pause right now. Go ahead and actually do it. Find a friend, find somewhere to draw some pictures, and talk with them. All right, I'm moving on, assuming that you've done that. Before I sketch the graphs, I actually want to show you an animation from Wikipedia. So here we go. This is an animation of this circuit. Capacitor on the right, inductor on the left, and that's it. As we can see, I wrote that LC circuits oscillate, and this is because the back EMF resists the stop in flow when the capacitor is fully discharged. So let's think about this a step at a time. There's a lot going on in this animation. Watch it a few times. But we start with a fully charged capacitor, which, is going to discharge, and it's going to discharge through the inductor. But as it's discharging, the current is building. It takes some time to build because the inductor is resisting that build, but the current is going to build. When the capacitor is fully discharged, the magnetic field through the inductor is going to start to decrease. But Lenz's law says that we're going to induce a current in the inductor that will oppose that change. In other words, the decreasing magnetic field is going to create an electric field that will continue to push charges in the direction they were going to resist the stop of current. So, capacitor is fully discharged, but the magnetic field creates an electric field that continues to push the charges through. And what ends up happening is we end up putting the charges onto the other plate of the capacitor. So if the electrons were on the bottom plate, the inductor pushes them on through to the top plate. And if the electrons were on the top plate to start, the inductor continues to push them on through to the bottom plate. At that point, we'll end up with a fully charged capacitor. That capacitor is going to discharge, and the cycle is going to repeat. This is an oscillating circuit. I know it can be a lot to look at animation, so let's look at some still images on the next slide. This is just the problem statement again with the circuit. And then here, I have some pictures at various moments in time. Let's start with positive charges on top, negative charges on bottom. Let's think conventional current. And so these positive charges flow around here and flow around the loop this way. That's shown in this first quarter of the graph, which is the capacitor starts with positive charge and it discharges to 0. And the current builds, and it continues to build until the capacitor is fully discharged. At this point, the current is going to start to decrease, which will create a decreasing magnetic field inside of the solenoid, inside the inductor. And that decreasing magnetic field is going to generate an electric field that continues to push the charge after the capacitor is fully discharged. So we can now continue pushing the charge all the way to the other plate. And so the top plate is negative, and that positive charge has coasted all the way to this plate here. At this stage, the capacitor is going to discharge in the other direction. Capacitor plate loses charge. Current continues to build. And then finally, the capacitor is fully discharged, but the current is flowing. And to resist the decrease in current, the inductor is going to continue pushing charge through until it ends up back on the plate it started. And it will do that continuously over and over and over and over again. Some features to notice here is that the way we've modeled this is that the charge time graph is a cosine curve. The current time graph is a negative sine curve. And these are the relationships you can expect. The purpose of this video is to show the ideas behind these circuits. Part of what I will ask you to do then is to look at differential equations and use some calculus to derive the mathematical expressions that go along with these ideas. Thanks for learning with me, y'all. I appreciate it.